Hello, this is Mike, and welcome to another Fusion validation. Today we're doing some interesting geometry. This is a toroidal shell with uniform internal pressure. The example, like all of them, I shouldn't say all of them. We could stray from that in the future, but it comes from Rourke and Young. This one from, if you have the fifth edition, from 1975. This is on page 454, table 29, case 5A. So it is a book validation model we're doing here. The model that we're going to do is 1/8 of an inner tube with symmetric boundary conditions at all edges. So if you take a look at the geometry here, you can picture how this is 1/8 of the geometry, right? If I complete the other three segments, then I'd have a full circular shape. And then we're just doing, say, the upper or lower half, depending on your perspective of that. So we're going to do a 1/8 model and then, of course, apply our symmetry conditions so that we get the appropriate results. Let's talk a little bit about some of the dimensions. The total outside diameter is 30.4 inches. So the way for me to look at that would be to do the inspect, and I'm going to select the outermost bottom corner of my geometry. And you can see that this is measuring its Z position along the axis from the origin at 15.2. So again, if I had modeled the 180 degree segment from this edge over to the opposite edge 180 degrees away, that full diameter would be 30.4 inches. And then we have an outside diameter of 10.4 inches. So that's going from this edge here to this edge right there. So we can see that that is 10.4 inches edge to edge. And then the thickness here is 0.2 inches. So let me grab that point, and we can measure the width or the thickness right there. That distance is 0.2 inches. To round out the dimensions of it, it's probably easiest if we take a look at the sketch. So let me go ahead and right click on the I need to close this measure tool. Let me right click on the sketch here, and I'm just going to say edit sketch, and I can show you what I started with. So again, here is the origin of our geometry. So out to the outside surface, if you will, that's 4.8 inches from the origin, and that arc or circle, I think I made a circle and then trimmed it, has a diameter of 10.4 inches. And then the center of that arc, the center of both the arcs, of course, is 10 inches over from the origin. So the the 10-inch over from the origin tells us where we need to make our circles. One diameter is 10.4, the inner diameter being 10 inches, and then where it's positioned or how far away from the origin, 4.8 inches to this point right there, meaning this right here would be 5 inches over. Okay, so hopefully that's clear. If you need to construct a geometry or if you are so inclined to construct the geometry. So basically, of course, I just made that sketch and then we revolved it for 90 degrees. So if you are going to construct this geometry yourself, you might want to pause the video, take a snapshot of that so that you can recreate the geometry. Pretty simple geometry to do, just revolving it around the y-axis. Then mine, of course, is sketched in the xy plane. All right, so I'm going to go ahead and finish this sketch, and let's get into the setup of the simulation. As far as what we need to do for the setup of the simulation, we're going to apply an internal pressure of 35 psi. Kind of irrelevant, but we'll apply a material of steel A36. And then we're going to look for a max stress of 1312.5 and see how close we can get to that result. So I'm in the design space right now. I'm going to go into the simulation environment. And we are still working on static stress analyses. I promise in some upcoming videos we'll get into some different analysis types, so it's not too far off in the future. So here we go, creating the study, static stress analysis. First thing I'm going to do is define my material. So it does have a steel material that's just coming over as a default material. Could certainly utilize that. You might have some different default sets. So let me go ahead and choose something. Let me set this to the Fusion 360 material library that it's picking from. And then we're going to scroll down and we'll choose a steel material. And if we scroll down far enough, you'll see steel ASTM A36. So I'm going to go ahead and choose that. If you want to look at the properties, you can click the properties button. And there you can see our density of 0.283, Young's modulus is 2.987, and Poisson's ratio of 0.3. So that all looks good. We do need to define basically pressures, constraint, and mesh is all we need to do for this model. So the constraints are probably the most tedious thing to set up. We do need symmetry conditions on 4 different faces. So this face, since it's facing me, let's start with that one. So for our symmetry conditions, because we've sliced through what would be a full model, we always constrain the translation perpendicular to that face. So if I look at that edge, rotate my mini axis a little bit, as I have the model oriented, I have that face right there selected, right? And I can see the axis perpendicular to it would be the X. So when I go into my constraints, I know that I can free up UY and UZ, and we'll say OK. So then we'll rotate the model around a little bit, grab the other face over here, and let's go ahead and do that. Select that face, go back into my constraints, make sure it only has one face selected. The vector perpendicular to this face that I just selected is the Z. So I'm going to get rid of UX and get rid of UY. There we go. All right. So on this face over here, the vector perpendicular is X. So that's my constraint. Over here on this face, the vector perpendicular is Z. So that's my symmetry constraint on that face. So that takes care of, for this model, stopping the translation somewhere in the model against translation in X and translation in Z. Since this is a static stress model, we do like to have a statically stable model. That is, that globally this model cannot drift off into space due to some load along the X, Y, or Z, or rotate about one of those axes. Well, guess what? Since we did a 1/8 symmetry, we sliced this model in half, top to bottom, we're also going to apply symmetry constraints down to those faces. And what's the vector perpendicular to those faces? It's the Y. So just with my symmetry conditions alone, somewhere in this model we've applied translation X, translation Y, and translation Z constraints as soon as I apply these next 2 constraints. So that makes this model completely statically stable without adding any artificial constraint to the geometry, right? So it's kind of a neat thing that we can do here with these symmetry constraints. So let me go ahead and select those faces a little bit harder. There we go, that face, and this one right there. And we're going to get rid of UX and UZ for that. So I'm just constraining again the translation perpendicular. All right, and we'll say OK. So there we go. The bottom takes care of Y, this edge right here taking care of X, this edge right here taking care of Z. And now this model is, because it's a single body, and at different locations on the model, I've accounted for basically all 3 translational degrees of freedom. So it's really kind of a neat thing. I know I keep harping on it, but basically, we're going to apply internal pressure to this, which is going to cause it to expand outward in all directions, but yet the model is still statically stable because of the symmetry constraints that we apply to it. So it's a really neat technique. I'm kind of a fan of it. So anyway, we'll move on from there. As far as the load, it's going to be a pressure load and 35 psi. So from the pull down menu, we're going to go in the structural loads, and we're going to apply a pressure. Select that inside surface, and it's going to be 35 psi. All right, so there's my pressure load, which will be applied radially outward. The only other thing that we need to do for this model and the setup of it is the mesh. So let's go ahead and right click and say generate mesh. And as I always mention, you can just go ahead and hit solve, and it'll mesh the model if you haven't already as part of the solving process. But I like to do it ahead of time and take a look at the mesh and see what I think about the mesh, whether I want to go a little coarser or a little bit finer. In this particular case, I'm going to go a little bit finer. So let me right click on that, and I'm going to go into mesh settings. And rather than using the slider here where I can move it towards the finer end of the spectrum or coarser end of the spectrum, what I'm going to do is tell it that I want to use an absolute mesh size. And we do this sometimes, right? We know we want a particular mesh size based on our geometry. So I'm going to go with about a 1/4 inch mesh size. And if I click on advanced settings, you can see that the element order is parabolic by default. So that's on. In addition to that, the create curved mesh elements is on. So because this geometry does have a lot of curvature to it, it's curved around its circumference as well of the what do you want to say, of the cross section, but it's also curved continuously around the whole torus, right? So this create curved mesh element says when you create the mid-side nodes to make these elements parabolic, put them along the curvature of the CAD structure. So that even increases the accuracy even more. So we'll say okay to that. And I get the little warning mark because I haven't regenerated my mesh. I changed parameters, but I haven't regenerated it. So that's going to go away as soon as I say generate mesh. And we'll do that. All right, so it takes a little bit longer, finer mesh. And there you can see that's what we have. But the analysis itself doesn't take all that long. So I'm going to go ahead and solve it. Let's go ahead and solve, and you can send it to the cloud. I'm going to save myself a couple credits and go ahead and solve it locally. This is one that should solve quite quickly. But you know, if you had multiple studies set up, different mesh sizes or different materials you were analyzing, maybe you have different loading conditions. You have to analyze several different loading conditions. So if you had multiple studies, maybe you send them all off to the cloud and let the cloud solvers do all that work for you, and your computer is free up to do other tasks. But all right, let me go ahead and close this. And what we want to do is find out what the average tensor in the y direction. In my case, the y is the vertical direction, so I'm going to take a node right there and an inside node and figure out what the stress tensor in the y direction is. And then we're going to average the inside and outside stresses to get what we're looking for. So over here by the legend, I'm going to change the type of output that I'm looking for from safety factor. Of course, I can change it to some type of stress or displacement reaction forces. We're going to look at stress. And then right below where we change the type of output, there are, okay, so you change the stress, but what particular type of stress do you want to look at? Do you want to look at von Mises or principal stress, etc.? So we're going to look at a normal YY stress. And we can already see that the max occurs basically right there in that location. What might be easiest for me to do is to turn on the mesh. I'm just displaying the mesh so that way I can see where my nodes are. And the other thing I'm going to do is turn off the deformation. A little bit easier to pick the points that I want whenever it's undeformed. So again, I'm going to select that corner, and we'll average those two results. So how do we do that? From the Inspect pull-down menu, I can tell the program that I want to create a surface probe. So that's saying I want to select some node right on the surface of my geometry. So there it is. There's the 1290 and one of them. And then I'm going to select this one right here. And technically I could do this even a little bit better way. Maybe I'll show you that too. Let's do that. Let me go and do this. Let's create a surface probe. Oh, no. We just did a surface probe. Let's create a point probe. And I'm going to create a point probe right there. Now, when you create a point probe, what you're able to do is give it actual XYZ locations for that probe. So you can see this is a very small value, 4.455 E-6. So that one should be 0. And then the Y distance is 0.012. Again, small distance. I want that to be 0. Just basing it on where that corner of my geometry is. And then Z, right now I have selected 4.809. I want 4.8. That, remember whenever I drew that sketch and I showed you those sketch dimensions? So that corner was 0, 0, 4.8. So let's say, okay, so now I have the result at that precise corner. And we can repeat that process. Let's go ahead and do that. Create a point probe. There we go. And again, X is going to be 0, Y is 0, and Z, remember the inner radius there, 5-inch. And I'll say okay. So there we go. Now we know that we're probing at those precise locations, and we can go ahead and take the average of our values. So let's type those in. 1290 plus 1383. We'll hit enter, divide that by 2 so we can take the average, and we come up with a value of 1336.5. Let's bring back our spreadsheet. So again, our target was 1312.5. In Fusion, as I set up the model, I'm getting 1336.5. Gives me a percent difference from the theoretical computation. My percent difference is 1.8%. So I would say quite a good result for that setup, and I'm pleased with that. And hopefully that's an interesting example, and hopefully you learned something new. Thanks for watching. Have a great day.